this a couple of months ago. Helen did, and said, "Hey, we'd love to have someone come down and speak." So Kevin is the fellow who made the trip down here from New York. He's been with me for I guess about 8 months now, but he's been working in low latency messaging now for the last 17 years. So he's worked primarily on stock exchanges up in the New York City area. So he's very familiar with that space in terms of being able to get messages through the pipeline as quickly as possible. Think about trading floors and how fast you need to be able to make that messaging happen. So he's going to be speaking to us tonight. He's going to show us how to build these. So Kevin, I'm just going to let you take it away. So go right ahead.
Sounds good. All right, thanks, Scott. So I guess welcome to Fire Forget, how to build a messaging-based micro app specifically for the IoT world. I think we've already probably mentioned this to everybody. We've got a $50 Amazon gift card raffle going on. If you guys want to participate, just send Helen an email. She's got some kind of black magic pseudo-random number generator where she picks the special thing out of the box, and you get to go home with a $50 gift card. A little bit of bookkeeping before we get started. I want to talk about our agenda. We're going to be discussing, since today's about messaging on IoT, we're going to be talking about some of the issues that we're facing in the IoT world. Then I'm going to introduce the X platform, and at the end of that, I'm going to try to marry together why the X platform is so good for facing these IoT challenges. Also, still on the bookkeeping front, I just want to talk a little bit about Neat Research. They were founded around 2008. They are headquartered out of Silicon Valley, and since their inception, they've been really interested in high-performance computing. Okay, I think that's it, so let's get to it. Some of the challenges that we have seen in IoT. As you suddenly travel and meet all the clients that you're dealing with, we run across these 5 or 6 major things, right? I'm going to sort of hit each of them individually. The first is compatibility and longevity. And what that means is when you are deploying things into a smartphone, into any of the IoT devices, you know, coffee makers, things of the sort, you're now releasing them into the wild. That means that people can upgrade their systems, they can upgrade their versions as they see fit, or they can not upgrade their systems. I still have friends who have the StarTAC flip phones, right, in the age of the iPhone. And the problem is, you still have to support that stuff. You still have to support versions of things that you have long ago decommissioned. Another issue that we're seeing is that another issue that we face is the standards, and really what we're talking about is the lack of standards. There is no guidance out there. There are no best ways of doing things that are out there. It's really the Wild West. There are some people like doing stuff in JSON, some people like doing things in XML, and some people like doing things in binary because, well, why not? Another big issue that we're facing is that we see a lot of people are trying to solve IoT problems using traditional architecture. And what that means is that they're doing things in a batch processing mode. They're doing things in, where they're counting time in seconds, minutes, hours, and sometimes even days. And the IoT world is all about milliseconds and microseconds, right? They're also, traditional architectures are also not very good at dealing with structured data, or are only good at dealing with structured data. They have not evolved into using unstructured data, at least not to the degree that one would hope in this particular world. Another thing that we're suddenly seeing that happens a lot is you're getting horizontal evolution. You get technology evolving out of pace with each other. So suddenly, not only is your cell phone publishing Wi-Fi data, your cell phone is dealing with near-field communication data, NFC, right? This is where when you're walking through Duane Reade and it realizes that you're in aisle 2, subsection 3, and it says, hey, look to your left, and there's some coffee, right? And these are two different technologies that we sort of have to figure out how to deal with and hopefully not just coexist, but complement each other. Right? Another major issue that we're going to be talking about is scalability and latency. This is one of the main points of our discussion tonight, so I'm just going to leave that one alone. And if anybody's been following the news lately, security and privacy. These are not the same thing. Right? Security is about data encryption. Security is about making sure that your data can't be read by someone. Privacy is about not letting somebody do signal intelligence. How many times did I open and close that refrigerator? How many times did my coffee maker turn on during a day? How many times did the lights turn on at midnight? Things of the sort. These IoT devices that are publishing information out, and you need to be able to mask that information. So this is such a huge topic that it's an entire talk. The reason I put a star next to it is because I threw up a quick slide to show that it's on our agenda, but we're not going to really talk about that today. So On the side of scalability and latency, here's some industry standards, right? Gartner says there's about 8 billion connected devices in 2017, and by 2020, they expect to have something like 26 billion devices. If each of these devices were sending only one message a day, right? In 2017, that would be that you would have to deal with 92,000 messages a second. And by 2020, you're in the 300,000 message a day range. Message per second a day range for one message. And we all know these devices are not sending one message. These devices are sending thousands of messages a day. Cisco, on the other hand, is estimating that by 2020, we're going to be transmitting 600 zettabytes of data a year. Right? In 2014, MLB already processed half a petabyte of data in one game. That's just an amazing amount of information that's flowing, and that means that we have to handle that. Another interesting little data point is that because we're talking about IoT, and because Cisco has insight into a lot of this stuff, we realize that location is about 70% of the data that's being transferred by devices. That means that these are all embedded devices that are collecting metrics of where you are and sending it with or without your knowledge. Right? 70%, Cisco's estimating that 70% of all internet traffic happening throughout the world is going to be generated by non-human behavior, by computer-related behavior by 2019. So in the IoT world, let's talk about, oh man, you can barely see it. That's terrible. I guess we'll just sort of muddle through. Let's see what we expect in the IoT world, right? We're going to talk about a smart city where you have a smart car, and your smart car is driving in a smart road, and it's living in a smart city, and you're inhabiting a world where you have smart lights, right? What's the way that your car, when you're traveling at 60 miles an hour, communicates with the smart city? Is it generates some telemetry, right? It matches up that telemetry, and it sends it over the wire, or the virtual wire. We'll talk about that in a little second. It sends it over the wire. That wire then hits its closest possible node, that then makes a decision, and then that forwards it onto another node, and then that node makes a decision. That at one point finally filters down into a intelligent traffic light that's sitting in front of it, that then makes some kind of decision, turns around, and does the exact same process in response. Right? And now if you've got two of these cars traveling together at 60 miles an hour in that smart city, what does that mean? That means that latency matters. That means that latency matters. Latency matters quite a bit. When you are traveling at 60 miles an hour, you can't wait for 2-second message response times. We're talking about microsecond response times. Another thing, and it's not as obvious as I'd like it to with this picture, another thing that we're tending toward is toward fog computing. Much less so the concept of, everybody here is probably familiar with the concept of edge computing, where you're pushing out your computational power as far to the edges of the network as possible. But what we're seeing emerge is fog computing, where you have many of these nodes making individual decisions, forwarding up to additional higher nodes where they're finally pushing it up to the cloud, but they're also going to be pushing it down to other embedded devices that are making that decision. So on the route of latency matters, it also means that routing matters, right? So let's say I'm designing a smart car that's driving in Phoenix, right? And my company is based out of New York City, and I actually have an office in San Francisco. Now, if I didn't do my job well, if I just suddenly say that, hey, because my main base is out of New York City, basically every time the car transmits a message, I've got a 63 millisecond round trip hop that takes transferring between Phoenix and New York, whereas if I was in San Francisco, it would have been 22 milliseconds. That means that you have to suddenly be aware of where you're going to be trying to send data, and that awareness has to change. Routing matters. Something that we've found as we are working in the world is that mobile data comes at a cost, and that cost is multi-tenant, right, or multifaceted. There's two kinds of cost. There's a monetary cost, and there's also a latency cost. The monetary cost, if you're thinking about how cars are going to transmit information, well, they're doing it over a cell network. And that cell network's not free. AT&T doesn't give it away. So, Verizon doesn't give it away. You're going to have a plan. Some people have 5G limited plans, and some people have 3G limited plans. And you're going to have to be able to take advantage of that. And you're going to have to realize what plan you're using. Because what happens if you end up having a plan where you can deal with 1 gigabyte a month versus unlimited data? right? You have to have agents that are able to take care of that. So suddenly, you're introducing intelligent actors into the connectivity system. And these intelligent actors are going to try to do very smart things. They're going to send reduced footprint when you're on a cell network, and they're going to do data dumps when you're on a Wi-Fi network, right? And now that you've got intelligent actors, you're actually adding in a larger part of the problem is that you're going to have sending strategy evolution. And now that you've got a sending strategy evolution, you've got multiple versions of sending strategy, and you have to be able to deal with all of those versions, right? This is one of the things that I was talking about originally, saying that you may end up having to support things that you've decommissioned long ago because of this version management. And not only that, because we realize how many cars are going out there, how many phones are going out there, how many places are collecting telemetry, we need to be able to handle these things at scales. And because it's the IoT world, and because we're talking about smart cities, smart cars, smart infrastructure, and will very soon become smart emergency response services, smart police, smart fire engines, smart ambulances. These systems cannot go down. There can't be a downtime so that you can upgrade your system. This is, I actually had one of my friends who was working in Motorola at one point, was saying that their client's really upset because they're going to bring down their entire communication system for 6 to 8 minutes while they upgrade it. I said, all right, well, that's not good. Who's the client? Australia. Wait, what? Australia's emergency services are going to be down for 6 to 8 minutes? And this is true. This is how things used to happen. And they would never tell anybody about it. You can't suffer downtimes, especially in the world of everything that's connected. All right, so far, that is what, that's our quick introduction to the IoT world. Now, I'm going to introduce what the X platform does. The X platform, man, I wish I could do this. My boss has such a good way of doing this. He is able to explain that the X platform is a memory-oriented platform for building multi-agent, transactional, Java-based enterprise applications. And he's able to say it with such gravitas and seriousness that people look at him sagely and nod and they, yeah, that's really important. And I'm just not one of those guys. So instead of trying to explain that, I'm going to show you what it does with pictures, right? The first thing the X platform does is it's a messaging-based platform. And once we start dealing with messages, right, we get a whole boatload of benefits, but I'm going to mention the first three. The first benefit that we get is routing, and on top of that, we get smart routing. We're not just being able to send an individual message. We're able to specify who we're sending a message to. We're able to specify what kind of message, and we're able to let people express interest in kinds of messages as well. Another thing that we've abstracted away, once you get into the messaging world, you get lost in the weeds very, very quickly. What kind of channels are you setting up? Is it pub sub? Is it direct communication? What happens when something fails? Do you roll back? It gets pretty complicated pretty quickly. We've abstracted that away. We do a great job in letting you just send a message. And that sending a message is guaranteed to make it to its destination. Well, we'll get to how that works in a little bit. That message will be guaranteed to get that destination. And not only that, we also will guarantee exactly once processing. Right? Exactly once processing is, think about failures in credit card processing systems or an IRS processing system. Does that mean that you had a technical glitch and you get billed twice? You know, you can't have that. You have to be able to guarantee individual processing systems. And the last thing that's unique about the X platform is we allow you to put your message handlers anywhere you want within your code. We basically let you decide how your code should be structured and look, instead of us telling you how your code should look. So, yeah, us telling you how your code should look. Because we're all about speed, right? We're really passionate about high performance computing. We keep all of our state as local POJOs. That means plain old Java objects. That means you're keeping your stuff in memory. We don't write to databases. We don't write to disk. We don't write to anything of the sort that's going to slow you down. And the second I tell people that, they say, well, what happens? We don't like storing things in memory because what happens when you have a process loss? What happens if your machine goes away? What happens in the event of inevitable failures? And we actually, part of our system is that we've made it highly available. And once you suddenly take away the concern of the memory volatility, once you're dealing with a highly available system, you realize that we've now made memory durable. Writing to memory is as safe as writing to disk. And because we've removed those constraints, because we removed those bottlenecks, we're able to work in a much, much faster fashion. Something you can probably tell based off the picture is we really strongly subscribe to the multi-tenant or multi-agent microservices architecture. And what that means is we ask you to break things up by function. That means do one thing and do it really well. And that's a lot, that's a lot easier said than done. And if you don't believe me, think about the commands of ls, set, and grep. These are arguably the most used and powerful tool sets in the Unix system's toolbox. And man, these things do not fail. And they do their jobs wonderfully, but they only do one job. Where the major value added from the X system is you can cobble a lot of this stuff together on your own, downloading stuff from the internet. The major value added is we do this while still being ultra performant. How performant? For example, some of our Wall Street clients that are dealing with equity trading, zero-touch algorithmic trading, are handling hundreds of thousands of messages a second in 10 microseconds while running in high availability. And the last thing is we give you, and I alluded to this previously, we give you smart routing, and smart routing provides horizontal scalability. This is such a big deal that I've actually dedicated a separate slide to it. That means that, for example, we're able to determine, you're able to set things up based off of individual keys. Say, for example, you want to add version numbers into your channels and your communication channels, how you communicate and where you send things to. But we also do content-based routing. That means that we're looking inside your individual message and figuring out what node to send that to. One of the ways that the way that we provide high availability is the fact that we're always running a primary and a backup node on separate hosts. We provide you the ability of running a tertiary node or writing out to a different data center if needs be for recoverability reasons. So now hopefully this makes a little bit more sense of the X platform is a memory-oriented platform for building multi-agent transactional Java-based enterprises. The only caveat that I would throw on top of that is the fact that it is performance-centric. I've got a couple more details, but I want to, does anybody have any questions at this point? Is there, nope? All right. Usually the first question that comes up is like, well, that sounds great. How do you make things highly available? And that's one of the things that I alluded to in the previous slide, is that we always run things in dual modes. We run things using a primary node and a backup node. And well, that's great, but how do you make sure that nothing's lost? What happens if you lose something between receiving a message from the messaging fabric up into the application header? Well, let's walk through how we do that, right? We first start out with the asynchronous guaranteed messaging bus. Now, these are the messaging buses that you can find out in the wild, things like Kafka, things like Solus, things like TIBCO Rendezvous, any of the MQs. We provide bindings out of the box, right? So what happens is, the first thing that happens is somebody puts a message onto our bus, right? And then we figure out where we're going to route it to. As soon as we figure out where we're going to route that to, we send that to the appropriate instance. That appropriate instance gets passed to the business logic. Now, this is your domain logic. This is your black voodoo stuff. This is the stuff that you guys know how to implement. And because we know what your messages look like, once you finish, and your state, sorry, your messages and your state, once you finish processing, we actually only copy out the changes to your state. And that gets passed to our ODS, which is our object data store. And our object data store is then responsible for making sure that you're writing, again, you can't tell what the color, sorry, but you're writing to a transaction journal log down there, and you're also offloading that into your backup system. So you don't actually have your backup system performing the same logic again, so you're not running into the split brain procedure, but you're having your backup system capture and acknowledge the changes to the state so that you can apply it. Once your backup system has acknowledged the system, this is what we call a stabilization method. Once the stabilization message comes back into the primary system, then and only then do we acknowledge the original message. That's the primary way, or the fast way of describing how we get, how we handle high availability. Now, this is a complicated enough process that people immediately say, well, we can't code for this because we've got a concurrency problem. How are you going to handle all of these threads happening at the same time? And what we do is we basically, this entire cycle is called exactly once processing loop, and it's single threaded per message type. So we take the difficulty of concurrency off the table. We want you to concentrate on your business logic. We want you to concentrate on the hard part, the stuff that we can't know, and we make sure that everything else gets taken care of for you. Now, sorry. Again, in the last couple of slides, I've shown 3 or 4 different things where we've got the memory state, and I say that this is a state management system where we're keeping things in POJO. That means most systems that are actually up and running, whenever you're trying to do a transaction, when you receive an ad transaction, when you receive a credit card transaction, people will slap that into a database, and then you want to do some analysis on that. And you pull a whole bunch of additional records on the database, sum them up, or do whatever it is you want to do. We actually want you to keep all of that stuff in memory. We want you to keep all of those states in memory. So suddenly the question comes back, are you keeping all of the state in the backup memory? And the answer is yes, we are. Right? That's part of your state change. As you're moving state from your primary to the backup, right? We're not doing the calculations. We're applying the delta of the state to the X application, and that's how you're able to track it. You want to actually keep all your stuff in memory. A good example of this is most of our clients are running with anywhere from small applications of 10 to 15 gigabytes to larger applications of 120 gigabytes striped out by ticker symbols, for example, on the NYSE exchange. And then people suddenly come back and they look at this and they say, well, great, you said to do things the Unix style, do one thing and do it really well. What happens if this is a catalog tracking books or something of the sort, and you want to apply machine learning to it? Well, it turns out we support communication to different microservices that will apply that individual piece of knowledge, right? So you take care of your domain knowledge and you send a message asking somebody else to take care of their domain knowledge. And does this impact performance? Not really. This happens in the microseconds, right? With Mellanox network cards and Arista routers and everything else, we're talking something along the lines of 2 to 4 microseconds per message. Right? On top of that, of pure communication, right? On top of that, you're going to deal with your processing time. And how important is keeping stuff in state? And it turns out that it's really important, right? For the people that are on the bottom of this scale, where you're dealing with the previous style of previous architecture, right? A mechanical disk seed is 10 milliseconds. If you're trying to do a remote data center read, you're talking 500 microseconds, and that's if you're lucky. That's if the remote data center happens to be next door, right? What happens if the remote data center happens to be in Chicago, right? That's a long. And a random SSD reads about 150 microseconds. Most of our clients fall firmly into this main memory where we're talking about 100 nanoseconds, all the way down to the L3 cache where we're talking about 12 nanoseconds. And some of our clients fall into this faster L1 cache where you're talking 1 nanosecond. Now these guys are doing a whole bunch of special stuff of NUMA control and accessing things, making sure that it's working correctly. But one of the things I was explaining this slide to somebody, to a non-technical person, they said, well, what is the difference? I can't tell the difference between a 10 millisecond and a 3 nanosecond. And so I whipped out a calculator and I did the response. And it turns out that we're on the order of, if 1 millisecond, or if 1 nanosecond was 1 second, the amount of time that we're processing from the mechanical disk seed is something like 11 days, or 10 days. Right? So you're literally talking 1 second to 10-day increase in processing speed. That's a lot. And what that's saying is that you really want to take care of your data management. You really want to take care of your state management and keep that in memory. Because the second you push that data management off to somebody else is the second those bottlenecks are going to strangle the latency of your application. So this is an example of one of the POCs that we ended up doing. And what I'd like to sort of explain is I'm going to walk through how it used to, what the traditional architecture was, and then I'm going to walk through what the microservices approach. Right? The traditional architecture, this is a credit card processing system. Again, apologize for the color. This is a credit card processing system, and what was originally happening, the request would come in, and that would be sent to the credit card master that would pull information from a database using the information on the message. It would then do some processing. It would then write the results back to a database table and then send a message to the merchant master, and the merchant master would then pull the results from that table, pull additional information from that message, and so on and so forth. This whole thing was relatively slow. We're talking in the order of 50, 60, 70 milliseconds. I don't know, much slower than that, half a second. Right? Whereas when we suddenly came in and we said, we're going to break this thing up into microservices. One of the first things that you can do when you're breaking things up into microservices is you can scale each of these microservices out on a different metric. That doesn't mean that each system has to do the best with the information that it has available. Each system can be tailored to use the information in the most appropriate way for itself. right? That also means that because, and so for example, this credit card master, we would end up scaling with 5 to 7 different nodes, and these merchant masters would have 15 to 20 different nodes. Right? The scaling is going to be different on a per microservice approach. And again, because we have this content-based routing, we're not sending an individual message to an entire cluster of nodes and saying, you guys figure out which one of you is the appropriate person to respond to this. No, we're looking at the message and we're sending it to the appropriate instance of that particular microservice. And also, please remember, these individual microservices are all running in primary and backup nodes, right? So there's never going to be a catastrophic failure of this. Another piece of information, another thing that's very interesting about the way that we went about building our systems, we support one-to-many or many-to-many messaging subscription. And that means that one message can kick off a whole bunch of different microservices happening. So now that we parallelize this, instead of the response time being the sum of all response times, right? We're now talking about the response time being the max of the highest one, right? You've increased the speed by quite a bit. And there's one more thing, because of this content-based routing, because of this dynamic routing that we've been able to add in, we're able to tack on things afterward. This means that we don't have to have figured out the system that we're going to be building beforehand. We don't have to design the stuff and figure what we're going to be using 10 years in advance, or 5 years in advance, or 1 year in advance. You can build these systems incrementally, and you can release things into production to test them out. This is something that happens very commonly with our algo traders, again, in New York. They want to try an algorithm out. They think it works, but they're not sure. They slap it into prod, and they enable it for one product. This means that you can enable things for 1 client, or 50 clients, or 5 clients, or 5% of the clients. You can do incremental release and testing. You can also do decrements, right, if you want to phase things out. One last thing about our system is the fact that we can't walk into every client and say your traditional architecture sucks, throw it all away, and use our system, right? You have to be able to integrate with traditional architectures on both the inbound and the outbound messaging. Now, what does our system look like? I keep alluding to the fact that we've got insight into what your message looks like. To what your message looks like and to what your state looks like. And that's because you don't write your own messages. You write your messages in what's called an application data model, which is an XML-based language. And then we take that XML catalog and we build the messages for you. And we spent a lot of time making sure that you've got incredibly efficient serialization. We support pretty much every kind of type that you're out there that you can think of, and we support compound types so that you can build messages on top of them. And this means that once you are ready to pepper your handlers around, you can actually put event handlers anywhere in your code, and that will be picked up automatically by the system. Again, you don't have to make your system work with ours. Our system will work with your code. It's the easiest possible integration. And here's the other thing. Remember this slide? I said routing matters. And this is really important. And it's really hard because this is great for designers who are going to sit down and say, well, this layout works if nobody moves, and nobody flies around, and nobody takes vacation, and nobody relocates. How do you deal with all of that, right? And in one of our upcoming releases, we're able to dynamically migrate state from your data centers, from different systems. As long as you have an X platform that is up and running, we're going to allow people to move. We're going to allow people to get on a plane and go on a business trip or whatever. And if you want, and it's so necessary, you can move state from one place to the other. In fact, this is one of the ways that if you want to migrate your entire data center from one place to the other without ever going down, this is a viable alternative for one of the things. Viable alternative to such a thing. Again, I just wanted to throw this up there, like security is on our radar. We do a lot of stuff about it. We make sure that this is as opaque to hackers as possible. But I don't want to spend a lot of time about it. That's a whole nother hour-long speech, so I'll just skip over that. I do sort of want to talk about the zero downtime upgrades we provided. We call them rolling upgrades. And one of the ways that we do that is we will knock down the backup, making the primary individual instance. We will upgrade the backup, and then we will knock down the primary. So as you can see, it just goes 1, 2, 3, 4, in which case you have actually upgraded your entire system without having any kind of downtime. And once you get into the migratory with the sticky states, this becomes even easier. Okay. Now, I came back to this point where I said, we ask you to write things in a microservices approach, and that's easier said than done. And there's a lot of reasons that's easier said than done, but primary reason, or at least from a developer's perspective. We'll throw in DevOps too. One of the primary, debugging them is just really hard, right? If you've got 5 different microservices sitting across 5 different machines, and you want to track one message that's going across all different machines, unless you've got GPU-enabled clocks, and by the way, those are only good down to the millisecond, right? Like, it's really hard for you to translate. You've got to log in, check your logs on one machine, log into the other machine, hope that you got the right time, maybe you got the right ID, and maybe there's not a bug going on. Like, debugging things across distributed systems is really hard, let alone managing distributed systems, right? Let's talk about some of our other clients that end up having hundreds of instances of X applications up and running. How do you manage that instance? You SSH into each machine, knock down the backup, SSH to the primary, knock down, you would be upgrading for a month. You can't do that. And we provide you a pretty complete tool set that's going to allow you to upgrade, do rolling backups, and bring up entire ecosystems. In addition to that, we allow you to inspect individual XVMs, individual processes. We let you look at the machine, and we let you look at the processes on that machine. We also, on a different drill down, we will surface those transactions for all of the running processes for the things that you're interested in. Does that mean that you can ask the XVM to show you the one message that's translated for all the systems? Absolutely not. You still have to do some work, but we certainly go out of our way to make your lives easier. We don't want you to SSH across 100 machines. We want you to be able to zero stuff in. We actually have a different, I have a different slide where we end up showing, we've got 75 different metrics, or it might be up from now, I don't know. 75 different metrics that are built in to each of our platforms. And those metrics are going to be things that are from ingest of message to egress of message, right? How long did it take you to unserialize the message? How long did your business analysis take, or your business handler take? How long did it take you to do the backup? All of these things are accessible through our Lumino dashboard. And there's one other problem that makes writing microservices difficult: administrative control. You want to build a checking system that checks your balances and everything else. That's great, but your administrators need to be able to query the health of the system. They need to be able to query how many users are there. They need to be able to add users into it. And you either have to build that messaging system in and try to create a separate channel and deal with configuration and control and everything else. Well, with us, you simply use some annotations. You can annotate your message, and these will be exposed into your DevOps systems as well. Now, there is a bit of hoops to jump through in order to do that, but we let you do it in a very, very easy way. All right, so I guess we're coming under a third point: why the X platform is good for IoT. And if you haven't noticed, I've sort of bled the why the X platform is good and IoT into the first and second ones. So instead of going there, I'm gonna hit the main points, right? Why are we so good for IoT? We're good because we provide a salient and a viable path for compatibility and longevity, right? We provide you the ability to do intelligent analysis and actions by keeping all your state in memory and by using separate microservices. We provide you the ability to handle scalability and latency. This is actually our bread and butter. And I know I glanced over it. We provide you security and privacy. What we don't do is we don't handle horizontal evolution. Whatever new technologies come out, we'll deal with them. We can handle their messages, but we're not going to help. We're not going to define new NFC protocols or anything of the sort, and we're not helping define standards. We're happy to use any standards that you guys want to use. We can consume those messages and we can process them, but we don't help define them. That's for large concerns like the fog computing concern. I think that's it. There's we've got some Git demos that you guys can download, and introductions to how to use Talon, some real basic, try to get you up and running within 45 minutes or an hour. Our core system, Talon, is free for anything up to about 8 gigabytes, and I think that about sums it up.
And it's open source and free.
It is open source. There you go. It's open source and free. Questions? Yeah.
First of all, will this be available online afterwards?
Yeah, we're recording it. I don't know. It's going to take us some time to, process and get it.
Slide deck.
Huh?
Slide deck.
Yes.
Yeah.
Yeah.
We'll get that on there.
Did you register for the thing I'm about to do? The drawing?
No, but I can.
Anybody that hasn't registered for the drawing, if you will just email a message to Helen, HELEN@needresearch.com.
We can just reply to all your emails with the slide deck.
Yeah, we can send it to you that way, and then also for the drawing. And then before you leave, there's a few little pins and giveaways over here, some webcam covers and pins. Hopefully you got a name? No? Oh.
I have a question. You said that you're writing information for the transactions in a journal.
Mm-hmm.
What information are you writing?
The changes to the reports and the gets, the changes to the objects, right? In fact, we provide some ancillary tools so that you don't even have to use the live data. You can, using that journal, you can reconstruct things live using a transaction log tool and see what's happening on a case-by-case basis.
That is for internal purposes.
No, that's part of your system, right? As your
As part of my system.
yeah. So like that journal, that journal is not logged by us. So this whole thing, we provide you with the X platform as a library, right? And that runs in your applications. That means it either runs on your premise, it runs on your AWS cloud. We're certainly here to provide help, guidance, consult, whatever it is you want, but it's your system, right? All the data, all the domain knowledge, all that stuff is owned by you. So that journal thing as well. You get all these ancillary tools where you can query state. You can, we were positing that we can actually use the transaction journal, right, as a compliance tool, because that's literally tracking changes on an individual field by individual field basis. What better compliance tool can you have than that?
So collecting data and using that data for analytics purposes or for whatever you want to use it afterwards, that's a very important part for machine learning, right? Because if you're going to be capturing that many transactions, they will, of course, because your audience, your system, you're going to be capturing that much data that it's relevant. And that's why I said, that's why I'm asking.
No,
It's
so
going to be private. Can I use it? Is it going to be for your purposes or for my purposes?
it's your data and it's your flow, right? This is how we rebuild systems. When unfortunately systems do crash, primary systems do go down. Sometimes that's why we have backups. And when you bring your backup up, you're not bringing it into a. We actually do two things. When you're bringing your backup up, you're not coming back to a pristine state and then trying to copy things over. You're actually, when you bring it up, you mark your place of where it's being brought up with the backup so that so that you know where to send the transactions, and then you run through your journal. So that when your primary comes back up, it has the previous state and it just copies over the changed transactions from the time that you began, and then you're able to, when you come back up, you're live. So that data is yours. That data flow, that message flow, that's all yours. Gets and puts, you can conflate them, you can draw, yes, gets and puts, you can conflate them. You can search them. We also provide you a transaction log tool that you can do searches. It gives you a SQL-based query engine. Yes?
So, because when I'm thinking about the size, depending on how much data
It gets big.
Okay.
It gets big. Like, if you're dealing with terabytes a day, terabytes a day are in your transaction.
So, you could ingest in the database for archive.
Absolutely. We provide, and that was one of the slides that I showed, we provide connectivity to any of your traditional databases, right? We can read and write from them. If you want to archive to them, that's fine. If you actually want to use them to seed your information, that's fine too. We can connect with them.
So how do you charge? Is it CPU basis, throughput basis? How does it?
How do we price support?
Pardon?
How do we price support for the open source? Well, first of all, the free version will give you up to, I think it's 8 gigabytes on heap for as many XVMs as you want. So you can have a cluster of really small things, but if you're doing like 4 terabytes or something, then you probably want to do the bigger configurations we have. And it is private sourced, so it's open source but in a private community just to protect the IP. There's a couple of patented pieces in there, quite a few of them. So we typically will price either by XVM or, not by CPU, but by XVM or by the amount of data. The interesting thing about the way, when we price by the amount of data, most of our customers pick that, because if you've ever worked with Java, you know that when you put data in memory, that Java stores like one terabyte of data in memory is actually like 3 terabytes of data in memory by the time Java gets done with it. We actually manage that, so we store by true memory. We price and store true memory. So most of our customer deployments that have just used, pure Java memory management in the past, they'll go from like 500 JVMs of stuff down to like, 15. It's an immediate footprint hardware savings for them. One of our largest banking customers went from over 500 JVMs for one of their trading apps down to 8, just to give you an idea of the magnitude of difference. It's huge. So, we try to make it as cost effective as possible. And one of the reasons that we kind of have done it that way is, one, because we're in growth mode. We're already profitable. So we're more interested in growth than we are in money right now, which drives me nuts as, somebody who has a lot of equity. The other aspect of it is that a lot of our customers have started because they need performance and they need scale and they need high availability. And okay, so our first applications are algo trading or whatever, but every single one of our large Fortune 100 customers have over 30 deployments. Any place and every place they can use this, they do, even if it doesn't require performance, even if it doesn't require high availability, because it's so much cheaper and easier to use to build systems and microservices. So, we market it as our differentiator is around speed, performance, availability, ease of use, but we're finding not the reasons that all of our customers use it. They kind of get hooked on it, and so it's like our own private version of crack, but it's open source, it's free, and we just want to see it grow. Yeah.
One other question. You mentioned Kafka. Does it compete with Spark as well in some ways? I mean, communication-wise, certainly.
It can use it.
Right.
Spark's not fast. Right?
Okay.
So
Yeah.
we have bindings for Kafka all the way down to 29 West, right? So the Ferrari of messaging systems, and you can use RDBMS and TCP. Like when you're interested in latency, that's not going to be an option, but we can definitely use it.